All right, we started. Let's do it. So today it's going to be total chaos. We're going to talk about a phenomenon that I think is very interesting, and unlike the last time, or last two times that I was here telling you stories, it's going to be something that we have some visceral feelings about. So before I talked to you about quantum mechanics, which is about things that are very small and are very far away from our human experience. Before that, I talked about relativity, which again is very away from human experience. It's about stuff moving very fast, close to the speed of light. It's about stuff near very strong gravitational fields. But today we're going to talk about chaos. And one of the wonderful things about chaos is that we experience it all the time, every day. In fact, some of my best friends are chaotic. No judgment, no judgment. It's a safe space, no judgment. So we all have some intuition about it, though we don't discuss it openly. So today we're going to experience some chaos and talk about it directly. And I think that another reason to sort of talk about chaos is that chaos is a very big part of the way that our biology has been shaped. So essentially, chaotic forces sculpt us biologically. They also, in fact, just as you are right now, you're being influenced by chaos. Inside of your bodies, there are all sorts of mechanisms that rely on chaos.
Somebody has a question. Can
Yes.
we make chaos?
What?
Can we make chaos?
Yeah, we will. It's going to be great. We have a chaos assistant. She's going to create some chaos today for us. So it's going to be coming. And so that's another thing about chaos, is that it's very much related not just to the way our bodies are, but also to our perception of the world. I mean, many of the sort of heuristic intuitions that we have about the world around us are actually coming from our experience with chaotic dynamics, which is what we're going to try to explain today. So these are all kind of important factors in sort of choosing this particular subject. And another thing I want to say is that, part of the reason I really wanted to talk about chaos is because we don't tell our children enough about chaos. And when they get taught in school, they have this completely unrealistic understanding of actually what our world is like. And because they have an unrealistic understanding of the world, I understand why. There's a certain reason why. There's psychological reasons why we don't tell them about chaos. But it messes up later the communication between scientists and society. And so scientists who have to deal with chaotic dynamics have problems explaining what it is that they're measuring and what it is that they're predicting to the rest of society. And that creates a barrier that really shouldn't be there. So the earlier children are exposed to chaos, the better. So that's another reason why I think chaos is worth talking about. I guess maybe I should say a little bit about why it's not actually presented in school, at least traditionally. So first of all, people didn't really begin to understand chaos until they really were faced with simulating the world. So in earlier centuries, they had physics laws, which I'll discuss today, and they didn't actually understand what those physics laws were telling them. And when they actually started to simulate things with computers, when they really thought about what is reality like when we try to make predictions, they were faced with all sorts of surprises. So that only started around the 70s and still hasn't made it to what I think should be part of actual curricula in schools. So that's another reason to talk about it. And in fact, there are very deep connections between chaos and computation itself. And so that's another thing too, that as computers become a bigger part of our lives, this connection I think is a very deep connection. So we can talk about that a bit more. So chaos has this dark and ominous kind of feeling. Here's a representation by some symbolist of what it is like to experience chaos or to try to walk through chaotic landscape. But in a way, I'd say that even though chaos sounds bad and sounds scary, it's actually better to face it and to try to understand what it means and to sort of break through to the other side, because in a way, once you accept what's happening, the actual reality is much more wondrous than you think it is. So you have to put away some of your preconceptions about the world, but in some sense the world is far more interesting, so it's better to know that ahead of time when you're thinking about physical systems. And for kids, I always think that it's better to tell the truth. It makes children better when they have to face the unknown. So let's talk about chaos. All right. So let me first kind of give you a little bit of the standard understanding of the world before chaos appeared. So before people actually started trying to solve things on the computer. By the way, you should always interrupt me with any questions mid-sentence.
Papa, why
Yeah.
did you erase my board?
Sorry, I want the white space. Okay, so here's the traditional understanding of the world. These are the lies that we tell our children. So Newton had this kind of approach to understanding the world. So this is a safe space. We start with happy pictures. His picture of the world was, okay, there's a bunch of stuff in it, and as we look at this photo, this little drawing, we all have some sense what's going to happen next. So each one of these figures is doing something, and we can sort of predict what's going to happen. She's going to jump up and down, the thingy's going to twirl, there's going to be some dynamics, and we all have an intuition for what happens next. Newton basically turned that intuition into math. And what he said was that if I know the list of all the initial positions of things inside of this picture, and if I know the velocities of how these things are, like how fast these things are all moving, then I could put it through this mathematical machinery and predict what's going to happen next. So basically, if I know where we are and we know where we're going, we can predict where we're going to be a short time later. He turned that into math. He wrote down a set of laws which have to do with forces or accelerations, and his machinery allowed the initial condition to turn into some final condition about the system. So he said, if I know where things are and I know where they're going, then I can predict where they're going to be in a year, in 3 years, in 5 years. It's all in my equations. Read my book. Okay, so that's what he said. And this kind of predictability wasn't just about objects in our everyday world, like solid objects, but it turned out to be also the kind of math that describes waves. So there too, the initial profile of the wave can be fed into an equation, which is the wave equation, and then you can predict the final profile of the wave. So again, if you know the initial condition of the system, you know the initial shape of the wave, you can feed it into a set of laws, and it will give you the final profile. So that was true about stuff that we could see and touch. It's true about water. It's true about various waves, like waves of sound. It's true about objects in this room. And it then extended to other systems where we can't see anymore what's happening. So for example, we can't see molecules of gas in this room, which are bouncing around and flying all over the place. But people realize that these molecules that we can't really see, they're basically equivalent to this picture that we had here, right? Like the math is the same. There's just a bunch of stuff, and it's bouncing around. There are a bunch of kids, and they're playing in some way. The math that describes this is pretty similar to the math that describes that. So even though we can't see this stuff, we model it in the same way that we model things that are familiar to us. And in the same way, when we got to the electromagnetic waves, which are light, we see light, of course, but we don't viscerally feel electric and magnetic fields. But the waves, the equations that describe electric and magnetic fields are actually quite similar to the equations that describe water. So again, it's a similar pattern. Question?
If light kept on going with nothing to stop it, would it lose some power, or would it keep on going forever if it had absolutely nothing interferes.
If it had nothing to interact with, it would keep going forever. It carries energy, and it only can give that energy away to something if it hits it. Just like waves in water. But waves in water have certain stable configurations called solitons that actually travel and don't lose energy.
Wait, will waves also go forever?
No, not regular waves in oceans because they interact with other things. But there are sort of kind of in some ways, in the same way that there are mathematical solutions that are kind of propagate forever. Technically, waves also have some mathematical solutions that have this property. But in practice, what happens is that liquids have friction and all sorts of other things. So so the water in some sense is more complicated than electromagnetic waves. Okay, so all these notions of predictability, of knowing initial conditions and finding the final condition were put together by this one dude, Pierre-Simon Laplace, okay, who formulated kind of the principle of what we call determinism, okay? So what is determinism? It's more or less what I've been saying. He said something like, if there's an intelligence, an enlightened intelligence that perfectly knows the present, knows every single object in the room exactly what it's doing right now, knows every molecule, every atom, perfectly is able to capture that, then not only will it have perfect knowledge of the future, because that was the structure of Newtonian law, but also immediately has perfect knowledge of the past. So an entity that perfectly understands the present is perfectly present. We're never always, that's the problem with humans, we're never fully present. But if an intelligence was fully present, then they would know both the past and the future. Yeah.
When was this like written? What time?
This is like 1750, I don't know, something like 40, 50.
Did they know about atoms at this time?
No, they didn't, but they had some notion at least of objects, and they had some kind of notions of, let's say, maybe that things are made of more fundamental ingredients. They didn't know anything about atoms, but they had this idea that they're just a collection of objects.
Well, the Greeks thought of atoms as an abstract theoretical idea.
Yeah.
What about heat?
Yeah, so they didn't understand heat, but they didn't understand how heat, heat is very important. We'll come back to heat, in fact. But heat sort of, they didn't understand heat enough to understand that it was kind of the same as energy. So that whole part wasn't worked out. So thermodynamics only became something that people really started thinking coherently about when they started building engines.
So they knew that there was some sort of fundamental building block?
Yes, actually, an atom is really like a Greek word. It's a logical idea that everything's made out of some kind of Lego piece.
So I understand the statement about the future, but was it really a statement of the past as well? Because you could imagine that you could come to exactly the same configuration in two different ways. He thought that that was not possible?
He did, so that was the confusing thing. So this is precisely what was kind of weird about it, is that, like, technically the structure of the equations does not tell the past from the future at all. And that already seems very weird, because it seems like our experience of the world, of course, knows the difference between past and future. And so it was a big confusion for them in some sense, like, why is it that the flow of time doesn't have a particular direction? Because technically, Newton's equations treat the past and the future identically.
No, but that's a bit different. I was wondering whether you could say, you could be in the present, and you
Yes.
could have some configuration, exact configuration of objects,
Yes.
which came about in two different ways in the past, and these two trajectories in the past led to the same result. So he didn't see that as an option. He basically
No,
thought that
that's not technically possible.
It's not technically possible.
In Newton, technically, if you know, because what I mean by measuring, there's a subtlety, because the input I need is both position and velocities, right? So the velocity is somewhat fuzzy, right? Because you kind of, in reality, you need to measure position. Yeah. So it's a little bit tricky, but let's assume that you have perfect knowledge. I mean, in this case, this intelligence has perfect knowledge, not just the positions of everything, but actually their velocities right now.
So knows
That-
vectors.
Yes.
Okay. So that would explain
That-
where
that's
we come
good.
from.
I mean, just to follow up on that.
Yes.
Can you imagine that something like comes into our solar system and gets captured and now is like in an orbit, couldn't you imagine that it was always in that orbit? Like,
No, because it would carry the history, if you knew its precise location and trajectory. I mean, you're assuming that you know all the laws, right? So everything, say, follows Newton's laws of gravity, and you know precisely its position and velocity, then you could, and the position and velocity of everything else it was talking to, you could roll back the clock. You could, you know, if you knew that precise thing. Yeah, we'll come back to how well we knew this.
Can I throw this?
Yes, you're demonstrating. Yeah, it's not bad. It's not bad, not bad. Actually, like, maybe we should give it some. Okay, so this, by the way, if you want to look it up, is called Laplace's demon, this intelligence. I never actually understood why it's a demon as opposed to an angel. Something psychological about, like, you know, like humans always assume that if you have perfect knowledge, you're just going to mess everything up or something. I don't know. I don't know.
No.
So,
I mean, I guess it's like free will determines.
yes, exactly. So this is also another thing that yeah, exactly. Good. So you're already seeing the issues with this. So it seemed like the past and the future are identical with this way of thinking about the world. But of course, as people are already asking, what about the flow of time? I mean, we don't experience the past and the future in the same way. So something must be wrong. And indeed, what about free will, right? I mean, there's so many self-help books. I mean, are they just all crap? Maybe they are. I don't know. That's a separate story.
Yes.
Right? I mean, if everything's determined, then there's no way to change. Okay. Okay. So these were kind of concerns that people had. And so now we should start actually asking, what is it really like to predict in practice the world, or the workings of the world? So let's start with some example that we all have some feelings about. We live in the solar system. Here it is. There's some asteroid belt. Things are orbiting the sun. Let's take a vote on the following question. Why is it that we can predict the motions of the planets around the sun? In some sense, which statement best describes why this is so? Is it because computers are awesome, man, and they can always predict the motion of objects unless there's like gazillions of objects? Then it becomes really hard. We run out of computational power. You know, we assume we know all the laws that and exactly how each of these objects affects each other. So do we know precisely what's going to happen? Or, okay, we can't predict the motion in general, but just like with 8 or 9 or whatever is the current number of planets according to some scientists, you know, we definitely have current computer power to predict what's going to happen. Or rather, is it C, that we cannot predict the motion of even a few interacting objects, but the only reason that it's possible is because we can ignore the effect of planets on each other. So this is most optimistic, sort of in the middle, most pessimistic. How many people vote for A? No. Wow, you're such cynics. Okay, what about B? All right. What about C? Okay, good, you're right. The answer is C. We suck, or life is complicated. So, in fact, the point is that we indeed cannot predict even the motion
My boy
of
has a
question.
What's a cynic speed?
I don't know. I don't want to break your child's heart. She's so innocent. I will let your parent decide whether she'll explain to you that word. It would be cynical of me to actually tell her what a cynic is.
Truth or dare?
Okay, so the problem is what is chaos? The problem is that the equations of motion have extreme sensitivities to initial conditions. So, where's my chaos assistant?
Right here.
All right. Okay, let's get our first chaotic dynamics. Let's get some light or something. All right. So what this thing is a chaotic pendulum. So Uma is going to start this chaotic pendulum from some position. Why don't you do it? Which position do you want?
I will do it from here,
Okay.
and I will ask you guys, where do you think it will go? Somewhere?
Into the middle.
Back and forth. It will go to the middle, but it will probably go into corner to corner.
You have to keep
It will go
consistent.
somewhere.
Okay.
Where it will go in the middle. Okay.
All right, let's watch. Let's just do it.
I knew it. I knew
It's
it
gonna
was
be
going
ellipse.
Is it? So should we start taking bets?
Oh man.
Is it? Oh my God! Is it alive? It's trying to decide.
It's magnetic.
I'm still taking bets. What? No. Did he think it's?
Magnetic.
Go around with somebody.
It's still going.
Okay, so maybe it decided on this. Did it? I don't know. Still making up its mind. Okay, maybe it's stabilized. I don't know.
But if I do it from
Okay, now do it from the same place again.
any other section,
Do you think it's going to go back here?
no, it's chaos.
It's chaos.
It's a
Maybe.
It's randomly
I think it's gonna go to the right.
Uh-oh. No, wait,
Wait,
no.
I'm gonna try to move it with my mind.
We all believe in you. Jeannie, if this works for you, I want stock advice. Oh my God. Oh,
It's
wait.
not there. It's in the middle because it's controlled by both of the markets.
Yeah, you're too strong.
Well, I guess it completely surprised us, like it said. It's chaotic. Okay, so this is precisely what chaos is. It's incredible sensitivity to initial conditions. So let me see if I can. I wanted to show you guys a movie.
I mean,
Yeah.
if you drop that from the exact same spot though, with the exact same thing, like a robot, would it always have the same ending or different endings?
If you dropped it from the exact same spot, it will have different endings.
Different endings?
Different endings. That's what chaos is. Let's see. Wanted to show you a video. Oh, but did I actually connect to the internet? Vita, what's your internet? Is it working? What is it?
Twinkie.
Twinkie.
Ah.
Okay, let's see. Does it know what Twinkie is?
Probably not.
No, it knows Twinkie. It loves Twinkie. Good. All right. So what am I showing you here? Similar thing. So all that happens is I'm going to. By the way, I highly recommend this series of movies about chaos.
Is it really?
So here we're starting with an arrangement of balls, and you're going to watch where the white ball goes, and it's going to leave a track. And the only difference between these two configurations initially is that notice this little dude here got slightly shifted by a tiny little bit. That's it. Otherwise, they're identical.
Hold on, slow down. Which white ball are you watching?
You're watching the cue ball.
Oh, could you full screen it?
Sure.
And you'll post the link onto.
We will post a link.
Okay, so watch what happens.
When we hit the cue ball,
Oh.
movement on both tables starts off the same way.
Oh, good. I don't have to say.
But after a little while, not too long, the trajectories become completely different.
Great. So you see, they're the same for now, but that tiny change in the initial condition caused the white ball to be in a completely different corner. So it's now here, whereas here it's exploring the territory in a completely different area.
If we want to predict the future of the cue ball, we can do so. But we need to know in detail the positions of all the balls on the table. And there are so many of them. A small uncertainty about a single ball shatters any hope of determining the future path of the cue ball.
Wow, great. I don't even have to say anything. So, questions? Does that make sense? It shouldn't make sense, but yes.
But this is saying if the conditions were exactly the same and we had some way of knowing it, the effect would be the same.
Yeah, right.
No. So, I mean, maybe in this, so maybe, like, we'll come back to that. There's a difference, yeah, let's come back to this. So here you're absolutely right. For this specific problem, it is true that if the conditions were exactly the same, then you would get the same thing. That I completely agree with. By the way, I wanted to show you what it looks like. So remember, we discussed the fact that we can't even predict the motion of a few objects. Not just like but a few, I mean 3. We cannot predict the gravitational trajectory of 3 objects interacting. So this is basically just a movie to show you what that looks like. Good choice of music, by the way.
I really, I like this.
Yeah.
It's a bit like our earlier table. The computer
Yes.
can calculate step by step the movement, but cannot predict the fate of the system.
Yeah, we can't even predict whether, for example, one of
Will the
these
small
objects
planet
will
one day
crash
collide
into
with
the
one of
other
the
one.
suns?
This is called the 3-body problem.
Can we predict with less objects?
So we can run the simulation, but we just run out of power eventually. So and the trajectory becomes very, very complicated.
So, we
It's
could
very
predict
regular.
the
So again, the only reason we
We
can
had
predict
infinite
orbits of
hosts.
things around the sun is
This is
because
not
we
the case
ignore
in
the
the
rest of the
world.
planets.
Because the sun is
Or perhaps,
so more powerful.
unfortunately,
Because the sun is so much more massive, yes. Otherwise, things just go haywire and are very, very complicated. Okay. So, so what I'm showing you here is actually true about most physical systems. It's not some kind of peculiar thing. Most physical systems that are free to move and explore, we cannot predict the future of what they will do at all.
So how do we dock in the space station?
It has engines. For example, have you ever thought, like, if we could predict the motion of satellites, why do they even need engines? You just launch them with a perfect trajectory and know exactly what they will do. But in fact, they have engines precisely because they have vibrations due to chaos, and we have to readjust trajectory all the time.
Close enough, right?
Yeah.
Yeah, we get them close enough because we know what the most massive objects in the game are. But there are always going to be chaotic effects that displace things by a little bit, which is why we need to, have a little bit of wiggle.
Wait, are you saying that if we knew perfectly everything, we could just have a spaceship going on gravity?
Yeah, I mean, in principle, you would think so, right? You would think that, if we knew the influence of everything, like, let's say there, we included all the moons and all the everything that's nearby. Newtonian laws, according to Laplace, right, are completely deterministic.
Wouldn't it be very slow though? Or?
To what? To calculate.
No, to travel. I thought that you said if you launch a...
But, I mean, in principle, people use gravitational forces always to, like, slingshot things. Or, yeah, I mean, you could try, the point is that it's not that when you launch, you can imagine launching and having, like, only 1 or 2 influences, and that would be enough. But that never works. You always need a bit more, like a few more engines to try to adjust for chaotic behavior. Okay, so indeed, we have very strong sensitivity to initial conditions, right? So that's one thing I want to say. But I want to say a little more. Can I have some lights? Because let's say you are a die-hard determinist, and one thing you could say right now to me, you could say, okay, but like when Laplace was making his statement, he didn't talk about practical predictions. Obviously, he didn't think about being actually able to know where everything is. He was talking about a mathematical idealization. He was talking about the idea that if there was an intelligence that knew where everything was, every single position and every single velocity, then that intelligence could predict it. So the idea was, if we lived in a simulation, and if I knew, because I'm simulating something on a computer, if I put into my simulation the position and the velocity of everything perfectly, shouldn't I be able to predict precisely what's going to happen in the future of that world?
Yes.
Seems very logical, right?
Life is not logic.
Life is not logic. Wow, that's not, well, I don't know, maybe that's a complicated statement. I'm not going to completely argue about this right now. So, how many of you have taken calculus?
I want to.
300 years ago.
I want.
How many of you enjoyed that experience? Well, actually, like a fair amount. So, I don't know if this will break your heart or not. So, calculus is a lie.
I always knew it.
Well, so let me try to explain this. So why do we say that we can predict everything? Like, so what do I mean by that? Well, that might be comfort to you. What is calculus? What is calculus? Calculus, so there's this trajectory here. Oh, it's actually perfect. I don't even have to draw anything. So there's some trajectory. And what does calculus say? How do we actually calculate this trajectory using calculus? Well, we take this trajectory and we actually break it up into tiny segments, right? And each of these segments, we just go on a straight line, and another segment which is straight, and another segment which is straight, and another segment which is straight, and we build up the trajectory from segments, and we make the segments smaller and smaller and smaller and smaller until we approximate this curve perfectly. That's what calculus says. But it assumes, light, I need light. Light is enlightenment. So they say the truth, the answer is blowing in the wind. So let's talk about the wind. Suppose you want to simulate the weather. What do you need to do to actually simulate the air currents? Well, you need to tell me in all of space how the air is moving. So you can't just do it. If you put it on a computer, you're going to have to decide how to encode that data on the computer. So you could do it in all sorts of ways. Like, for example, you could choose, you could be like square guy. And you could be like, I'm really into squares, and I'm going to choose squares. And these squares are going to be my idealization of space.
Ati, is there limitations of just like our formulas for the weather, on Earth, for example, or our computing power, or both?
Well, I'm about to answer that question. So first of all, I'm trying to tell you what the answer is in an idealized world. So again, you're trying to do calculus. You're trying to break up space into some discrete set of bits, and then you're telling me the velocity of the air currents on these little places, right? And you chose squares, but you could also be somebody else. You could be triangle girl, for example. People use triangular lattices all the time, so you could have a completely different lattice, where you are actually creating these sorts of triangles.
It looks like only girls can draw triangles.
That's true.
Yeah, they can.
Can you also be
You want me
groovy?
to help you?
Well, I can't draw, but
That was the last one I was-
it's a lot of, imagine a lot of triangles. So you could choose a triangular lattice, you can choose a square lattice, and basically what is the promise of calculus? Well, the promise of calculus is that it shouldn't really matter. Once your grid becomes very, very fine, it doesn't matter if you're triangle girl or square dude, you're going to predict the same kind of trajectories for let's say, in this case, the wind, the directions of the wind in our world. But precisely because of chaotic dynamics, that's not true. They're not going to agree. They will start agreeing, just like the trajectories of the two white balls agreed for a while. But eventually, it's going to diverge. Eventually, the prediction of square dude is going to be very different than the predictions of triangle girl, if the system is chaotic.
Who's correct?
In other words, calculus is a false promise in a chaotic system. In a chaotic system, it's not true that you can break up evolution into tiny chunks or space into tiny chunks, and the algorithm for calculating the future will converge.
Is that also probably the spaghetti model of the hurricanes? Like they do different lattices? Is that
They do different lattices, exactly.
I see.
So if you're a diehard determinist, you actually have to ask yourself, what do you mean by that? I mean, the math equation looks deterministic, but the math equation is actually an algorithm. And what you really want is not the stupid math equation, which is some idealization, but you want to have an algorithm that converges on the prediction of the future. And in a chaotic system, there is no such algorithm. Yeah.
Okay.
So nothing is simulatable.
Okay. So
That's what
my question is, okay, this is my question. Isn't the system only chaotic because there's other forces that we just haven't included yet?
No, because my claim is not this. I'm assuming I know precisely the evolution of everything here. Like my laws are perfect, right? Like here the laws were perfect. It's not that I don't know what the laws are doing. It's that I have no algorithm that converges on a unique answer.
Is there no world like that square guy and triangle girl acts the same? Is there no world like that?
Well, there are systems where triangle girl and squared guy would predict somewhat similar realities because the dynamics isn't very strongly chaotic or it's somewhat smooth. But there are other kinds of initial conditions, like when things are very turbulent and foamy and like messy, where they're just going to disagree what's going to happen.
So most situations they're disagreeing.
Most situations with enough things that they're going to disagree.
So let's say we went 5 minutes before this.
Yes.
If we run the clock again, something different might happen in our world than is happening right now.
Exactly. Because there's no unique past in the same way as there's no unique future in a
So
chaotic
is it
system.
true for a two-dimensional system that the calculus works in 2 dimensions?
Sorry?
So calculus works in 1 dimension, but because there's only one way to cut the
Yes,
line?
yes, exactly.
But then as soon as you go to 2...
As long as you go to 2, it becomes, that's right.
What's wrong with
Is there a certain probability?
Good, good. You're starting to think about the right, in the right way.
Wait,
Yes.
I mean, but in calculus, right, if you have square guy and triangle girl and
Yeah.
something, say 5 minutes out, things start diverging,
Yeah,
you say, okay, let's go back, let's make triangles 10 times smaller.
right. Right, so you're right. So you can make the triangles 10 times smaller, and again, they're going to agree for some amount of time, but then they're going to disagree later. And the problem is it's an exponential challenge. Okay, so it's exponentially hard. Like I could always pick a time over which, I mean, I guess we can argue about Moore's law, but like, a time scale over which we would have to have orders and orders and orders of like say I could predict the weather reliably for 3 days or 4 days now, but that's actually a lie. We don't predict the weather by actually simulating things without other priors. But let's assume that we could. Then, if I go out 1 month, it's exponentially longer. A year, there'll be a time over which almost any civilization will fail. Yes. Question?
I have a question. So if you may be transmitting this, recording it, and if let's say President Trump is watching this on Twitter, right?
Yes.
And finding it fascinating.
Yes.
And do you think he might intuitively feel justified in questioning these highly educated scientists that claim to predict climate change
Good,
80
good.
years in the future?
Exactly. Very good. So
encouraging him?
exactly. So that's exactly the problem. That's exactly the problem because we teach our children incorrectly because they're told to solve problems that have a well-defined answer, and everybody thinks that a prediction is actually a detailed history. But that's actually not what's going on. So that's what I want to explain. So here's the deal. So we have to make peace with the fact that we will not ever be able to predict a history in a detailed way. For the future. So here, but now let me take out Exhibit B. It's a coin. All right. We all have seen coins.
Heads.
Is this chaotic?
Yes.
Yeah.
Yeah.
Yeah, it's pretty chaotic, right? I mean,
Wait,
it
what was the
depends.
thing?
Predicting if
Heads.
it's heads or tails. It's pretty chaotic, like this, right? It depends on the precise force I put on my thumb. It depends on air currents in the room. It depends on precisely the surface that it falls and like its angular momentum as it's spinning down and all sorts of things.
The fact that it depends on so many things doesn't make it chaotic. It will still be not chaotic and depend on all these things.
It's chaotic. But I can ask a very different question. I can ask, what's the probability of heads versus tails? 50-50. How come you're so confident about it? Think how amazing that is. I just told you that we cannot predict the trajectory of this coin, yet all of you were completely confident that the probability of finding heads or tails is 50-50.
Yeah, but even children know that's not true.
calculated parameter.
Even children know that if you flip it 5 times or 6 times, you probably won't get 3 heads and 3 tails.
Absolutely, but if I flip it like, let's say 100
No,
times,
right.
then square root of n, whatever. We
Right.
can become,
Yeah,
in fact, I'm about to show you an experiment like that we did with E.
If you flip it, it's not going to be 50-50 because it will reflect the way you flip it.
Because it is chaotic.
But because it is chaotic, it's not, doesn't just depend on me, it depends on many other things. So I mean, this intuition that you have about the coin, so it is telling you something about the kinds of questions that you're allowed to ask in a chaotic system. So for example, when you came into this room today, did you ever think, oh damn, I should really choose the part of the room with more oxygen because I don't want to like faint or something or pass out during lecture? That would be like embarrassing. I mean, you can still pass out, but for other reasons. You know, I mean, or were you like, hey Vita, like, where was the oxygen last night? So that you kind of know what the initial condition was, so that you can make your determination where it would be best to sit.
Well,
did that come up like in your head?
I'm sure if the media told us that, then we would.
Maybe you would. Maybe it would be like constantly going to your neighbors and asking what they're doing with the oxygen in the next door apartment. But you have this intuition that doesn't matter. The same way that you had this intuition about the coin. You had this intuition that things spread out, that somehow oxygen is going to be randomly distributed, that the coin is going to be 50-50. It's going to explore its options in the most democratic way that it can. Thanks, chaos. That's actually chaotic dynamics. That's actually what chaos says. So let's try another little bit of chaotic dynamics. Where's my chaos assistant? Okay. So where is your? Let's test your intuition about the oxygen. All right. This is water.
Is that like nearly a thousand? This is food coloring, by the way.
Yes. What, you wouldn't choose blue?
Which color do you guys want?
Blue. Obviously.
Okay, green.
What are our choices?
Doesn't matter, it's all blue.
All right, so Uma's gonna drop some, not, just, can you do it like closer? Like 2 drops or something.
Yeah.
2. Okay. So,
That's so awesome.
and what is your prediction is going to happen with this little beautiful cloud with all its filaments as time goes by?
So it can spread out and float downwards.
Yes, it will reach the cloud, but you know, in principle, there's a little spot, like I guess you can't see it, but if you look up top, I can tell exactly where I dropped it
Yeah.
right now. Will I be able to tell in half an hour, maybe when this lecture? No. So somehow chaotic dynamics here is forcing the ink to explore all possibilities. Okay, so we're going to come back to that, and we're going to try to understand exactly how to think about this.
And this
Okay.
is where I don't understand the Laplace thing, right? So if you not situations like this,
He thought about it, but I don't think he really understood it. So that's kind of the point. So let me show you just another. Yes.
All the examples you're showing here, they're not chaotic. We just don't know all the factors in them.
Yeah, exactly. That's what I'm trying to see. What would be his answer to this? Would it be that we can't see well enough?
Well, so what I'm trying to walk back is the statement. So there's a lot of sensitivity to the initial conditions. And in his mind, and in fact the mind of a lot of scientists, including, let's say, people who were upset about probability showing up in quantum mechanics, they thought like Laplace's demon. They thought, okay, yeah, in reality we don't know the initial conditions, but if we actually could simulate it, we would. But I'm telling you, it's even worse. Of course you don't know the initial conditions, and because you don't know the initial conditions, there's always a physical error on your measurement of the initial conditions. You will never be able to predict the future, because there's a sensitivity to the initial condition eventually. But it's even worse than that, because you don't even have an algorithm that would essentially predict the future. That's what I'm trying to say. Even if you knew precisely where everything was.
The answer is like in half an hour you're not going to be able to tell where you put the drop.
Right.
So there is no way to tell. There's no way.
There's no way.
Like no matter what you know about all the molecules in the liquid, you cannot tell. Or you think that there's a way to tell if you knew but you just don't know.
So I'm saying that if you knew, so Laplace's demon would have told you that if you measured everything perfectly within this column of water, you could figure out where the initial condition
So we
was.
just thought we can't see well enough all the little details, so that's why we can't tell. But
It's worse than that, right?
It's a memory. Yeah?
It's a memory, but it's worse than that. So not only can you not tell because you couldn't simulate it back, right, in practice, because you would be incredibly sensitive to the conditions that you found it in, physically, but also mathematically, if you actually idealize this as a perfect container where you know where things are, you couldn't simulate it backwards because, as I said, it depends on your algorithm of simulation.
But Avi, these are three different things, not two, right?
So?
Because there's three different things, not two. You're sensitive to initial conditions, your tools don't allow you to approximate, and really, if you had been able to approximate, you still get different outcomes.
Yes.
So there's three.
Yes. Like, all of these things are related.
Wait, I mean, are you essentially you're saying that you can't have a Laplace demon in practice because you can't make accurate calculations, right?
Exactly.
Everything is sort of has a finite.
Right. Because my criteria as a physicist is not whether there's a mathematical symbol that says that things are well defined, but rather I think it's a little bit metaphysics, right? Because in practice it's already bad enough that I'm sensitive to the initial conditions, right? So then I can't really, in practice anyway, do this. But I think that it's important to also say that there is no algorithm. I actually think it's important when you think about reality to actually ask whether you have an algorithm that converges to the answer. So that's kind of my perspective. But you could take a different philosophical perspective.
But from the point of view of Laplace, right, if you have infinite precision in everything, then you can do it.
Right. But the question is, what does that even mean, right? So this is not what Laplace thought, right? He didn't think that it would require infinite precision in calculation. He thought that all you needed to know is the initial condition infinitely well. Yeah.
Can I ask a very unformed question?
No one
You're saying you know the equation, but you don't know the algorithm. So
right.
What's the definition of algorithm? Is it essentially your ability to divide the equation?
It's your ability to turn the equation into like a prescription, like a procedure that will tell you what the equation predicts for an answer. So in calculus, it means that you should come up with some algorithm that will predict the future, right?
In a finite amount of time.
Yes, in a finite amount of time.
Is there a way to see before it actually happens, to see the shades of colors of the color that you poured into the water? Is it possible to see where each shade will be?
As you see, it's getting more and more mixed up, so it's becoming harder and harder and harder. So in the beginning, you could kind of tell, you could look at it and you could actually tell where approximately I dropped it and you could find it out. But as time goes by, what happens in chaos is that it's just mixing everything more and more and more, and eventually it becomes just computationally impossible to retrace what happened.
So you, again, you're using computations, but before you said that is Laplace wrong?
Yeah, exactly. Could you tell us do you believe that in half an hour there is some signal there that if we had infinite resolution and infinite computational power and infinite anything, like we would be able to actually still deduce where you
Yeah, but that's.
But you think that
I mean, that's, I don't
Because
know, but to be honest, I don't know. It's a metaphysical question, right?
Yeah,
Because I
exactly.
don't actually know what math means if I can't turn it into an algorithm. Maybe I'm taking a very particular philosophical stance, but that's what it's meaningful to me, right? Math is meaningless if it's symbols. I want to, you know, as a physicist, I don't care whether you have symbols. I care whether I can translate these symbols into an algorithm that gives me an answer.
But there's a practical application, right? And that is when we get better precision, when we get better predicting. If
But
yes, then there's no indeterminacy.
But we don't know.
But it's exponentially hard.
I mean, look.
Right, so you're gonna, you know, it's sort of like saying, yeah, if the universe was infinite and I had infinite, I mean, it's just kind of like very Gedanken. It's almost like not really useful.
Yeah, sure, the answer exists, right? It gets better and better at predicting.
Yeah, but we'll
Well,
never,
that's
it's an
all you can predict for a day.
exponential, but it's an exponential
Yeah,
problem,
yeah,
right? So
yeah.
you can multiply your computational power by, I don't know, by factors of hundreds, but you're still gonna basically double or triple just the number of days that you can handle, right?
What I'm confused about is in math, you know, you can have the answer being 6, right?
Yes.
And you could have gotten this answer by 2 plus 4 or 3 plus 3.
Yeah.
And there's no way for you to tell how you got this answer once you have gotten it, because it's the same answer no matter what. And so the question is like, there's mathematically, it's entirely possible that with two different
No, not with a differential equation with two initial, like if you have a second order differential equation with, I'm sorry, you're asking me a technical question, I'm giving you a technical answer.
Exactly.
A second order differential equation, even a partial second order differential equation with initial conditions on the variable and the derivative of the variable is completely deterministic.
So that's why it's so hard.
Okay, good. So I finally, I didn't want to like, because we're going to go. So yeah, it's a very mixed audience, so I have to figure out like what it is you're asking me. Okay, good. So here I'm going to show you a movie of essentially kind of first chaotic dynamics. So where is
Let's
the?
observe what happens.
Why can I not? What is it?
Two evolutions
Did
are
we
almost
change the
the same.
resolution? Why is it not allowing me to?
It's fine.
It's fine. Okay.
Go full screen.
Oh yeah, I'm trying
Press
to.
F. Press F.
Oh, there we go. Good. So first, like we're just saying chaotic dynamics, right? Meaning that two. So okay, I should explain what we're showing you here. So what this is actually, you probably heard the words the butterfly effect, and the butterfly effect has actually a complicated origin. It's first because it was said that the flap of a butterfly's wings in Brazil affects, let's say, the weather in Boston eventually, which is true. That's what the statement is of sensitivity to initial condition. But it's also related to something I'm about to show you. So the first kind of place where people technically began to see chaos is when they were trying to simulate the weather with very simple equations. So this is a three-dimensional situation where each one of these axes is supposed to represent some sort of aspect of the weather. So let's say this is temperature, let's say this is like pressure in some point, and let's say, I don't know, this one's like the density of the air. And so these equations are, every single point in this trajectory is actually the condition of the weather system right now. So this is like a weather system characterized, let's say, by three numbers. Okay? So as this thing is exploring, so essentially we started the weather, like, in initial conditions of temperature, pressure, and density, let's say, which are slightly off, and now we're watching it evolve, so it's chaotic, meaning that, like, even though we started these guys very close to each other, eventually they'll just start diverging. So, okay, we've seen this over and over. But now we're going to ask a slightly different question, right? So we were motivated more and more to start thinking not about actual histories, but rather to think about probabilities. So what we're going to do is I'm going to show you something amazing, the miracle of chaos. So I'm going to now start the weather in completely different places. So these initial conditions have nothing to do with each other. So the yellow and the blue ball are different conditions, different initial conditions, yet watch what happens as they evolve.
They do not start from very similar initial conditions. Let's erase, say, the first 10 seconds of the movement, and then let's observe what happens.
Strange attractors.
Strange attractors. So eventually they're going to fill out the same distribution, basically, the same part, the same way that oxygen fills out the whole room, the same way that this fills up the whole thing. These guys are going to completely fill out the same shape, even though they started with completely different initial conditions. So that's the miracle of chaos. Chaos is not about detailed histories. Chaos is about finding the same probability distribution for things. And that's why there's this disconnect between what Trump says, because Trump wants an answer for a history. But what science predicts is not a history. It predicts a probability distribution.
Wait, can you repeat that?
Yeah.
Let me show you again. I want to show you another video which actually makes that very clear. Let's see. Just
By the way, if I had a penny for every time they called Trump chaotic, I probably could buy a house in Boston.
Okay, so what we're going to see is, so this is the butterfly. So the butterfly also came because of this particular shape that they discovered in this particular set of equations. So what we're going to see now is we're going to ask a different question. We're going to say, we're going to play like climate change. So let's pretend that this thing, this dynamic is describing our climate. And let's say whenever the climate crosses the zone, we get a hurricane. This means, this little yellow ball means that in this zone, this means hurricane. So we're never going to predict when we cross the zone, but we can ask, what's the probability that we are in the zone as we cycle through over and over and over time?
The results. Occasionally, a hurricane occurs.
Oh, actually they chose hurricane. Great.
When the trajectory enters the ball. Let's measure the proportion of the time between 0 and t when a hurricane rages.
Okay, so first it's just starting with some random thing, right? It fluctuates depending on whatever is the initial condition. But then, after a while, the proportion of time that it spends in the hurricane begins to be more and more and closer to a particular constant. It converges. What converges is not the history, but rather the probability that a hurricane will occur. Okay, so let's I think.
So it spends whatever 5% of its time.
Yes, and now start with a completely different initial condition.
Different initial condition and do the same calculation.
Right. You start completely differently.
Again, the trajectory spends a certain amount of its time inside the ball, and the average tends to eliminate.
But it tends to the same
How
thing.
about that?
Thanks, Chaos. So what happens is that probabilities converge. So actually, even though Triangle Girl and Square Dude are not going to agree on the history, if they did everything correctly, they will agree on the probability that events will occur.
What does that history mean?
History is a concrete sequence of events. Like, for example, the hurricane is going to happen on Thursday. That is impossible to predict.
Yeah.
But the statement is, given a year, how many hurricanes do I expect, on average, is going to converge? So with time, the more time you have, right, the more it's going to be true.
Data you have, or is it time?
What?
More data, or does it have to be time?
Time. Time. So the more time passes, the probability begins to
So
settle
you're
down.
using different data sets.
I'm
Like
using
triangles
different.
and squares.
Yes, if I'm doing this square, that's right. So in this thing, I don't know what they did, but if you used triangles and squares to simulate your system, you're not going to agree on the particular configuration at some particular time.
Yes.
But if you ask, how often does something occur at over a long, long time, both of them will agree. In fact, that's what we mean by actual prediction in a physical system. All right. So let me show you. Something else that you could sort of do. All right, so let me erase the.
Wait, Andy,
Yes.
you also said that we don't actually predict the weather by just running simulations.
Right.
How do we predict the weather? I know this.
So it's a complicated because you're exploring the space of probability distributions. You also measure the probability distributions. So you feed. It's a complicated thing of you simulating stuff.
Yeah.
But it's also you measuring certain probability distributions and using those as input to your simulation. And the probability distributions, you actually, you put up like whatever satellites or balloons or whatever to input that.
So if we know there's a, wait, how would that be used?
It comes into the prior of how you think, like what initial conditions should be or what sorts of things happen during evolution.
Okay, what went on from my weather station to tell me that tomorrow in Brookline, it's going to be 20 degrees Fahrenheit?
With some probability.
Yeah.
So what they did is they simulated the system with with different lattices.
Different lattices.
With different lattices. Moreover, they use some probability distribution that they have measured about the world, which already gives them some statistical uncertainty, some indeterminacy. And that feeds into the way that they determine what happens. So, okay, let me show you another, so this is what I'm saying. So we can't predict detailed histories. We can't predict what happens. Instead, what we can predict is the likelihood or the probabilities that certain events or configurations will occur. Okay, so let me now tell you about an experiment that we did with Uma. So, by accident, because my office is a complete and utter mess. What happened?
It's very chaotic.
It's very chaotic, but in particular, it also contains like a crap load of coins. And so one day, Uma started arranging the pennies according to the year. Okay? And she put more and more and more pennies, and because we started seeing some very surprising things, all of the nerdy postdocs got excited and brought us more pennies and more pennies, and eventually we wound up with this distribution here. Okay? Why is this? I thought we had better resolution before. I don't know what happened.
This is probably a later thing.
No. It's just like somehow the resolution on the camera changed or something.
Well, you close the laptop and open.
What?
You close the laptop at some point.
Yeah, that was
so
that.
it probably switched to something else.
Oh, yeah, I
This
should
is
have done that.
of each of these.
Okay, so each of these is the number of coins at a particular year. Right? So this is like, I think we did this 2 years ago, so this was like 2018, this is 2015, you go back into the past, and you have all this like set of coins.
Our earliest coin was 1945.
Yeah, 1945. So we wound up getting like pretty good statistics. Now, if you didn't know about chaos, you would have like said, what the hell should I compare this to? Does this depend on like, I don't know, where I had breakfast yesterday, or where the postdocs decided to buy a sandwich, or where they decided to go see the movies? Is this like a history of something very specific? Well, it seems like if you didn't know about chaos, that's what you would have said. It's some particular history. I don't know what it is. But because of chaotic dynamics, like as we said, it's just trying to explore all the possibilities that you allow it to explore. So what can it possibly explore? Like, I'll give you a clue. This thing is 2009.
Huh.
What is it exploring?
The economics.
The economics. Here's the official Treasury data. Look at this. Here it is. This one's here. Now, of course, we lose coins over time, so there's like a crunch, like an exponential this tail. But even this thing is here. This is the savings and loan crisis. You have people who are who are, it's right here. There's that structure there. You see this and that. Here's this and that.
What is this data on the right?
This is the official number of pennies coined that year.
On the right, 2009.
And this is 2000, that's right.
Okay.
So this, I'm not an economist. I don't know what determines like, you know, these peaks and valleys. It's people who decide like what to do with the economy. I can't, I know that they, like 2000, which is right here, they decided to stop printing as many coins because the internet economy kicked in. But like why there was no coins made during the recession, I don't know. But I can say I looked at the data back to the Great Depression, and at least during the Great Depression, there was also a hole in the number of coins.
To control interest rates.
Yeah. Okay. Great. So we have an economist in there. Okay. Very good. Thank you. So I you know, but the point is the following: the fact that this thing, this experiment that you can do with your like kids just by gathering coins, the reason that this correlates with the official data is because the coins are exploring all possibilities, giving the limitations, which is how many were printed that particular day. So that's why statistics works. Okay, good. All right. So essentially, distributions are what control the world. So we never actually want to predict the actual history. We want to predict the distributions. For example, this is the distribution of velocities of the various molecules, the nitrogen molecule in this room. This bump is set by the temperature of the room, which is room temperature, and that tells you what the probability of finding molecules with certain velocities are. And if you went out and you measured it, you would agree with this curve, not exactly, of course, in the same way that our coins did agree exactly with the treasury data, but pretty damn close. So when we make predictions in science, so for example, people study the distributions of galaxies. Can they actually predict the detailed distribution of galaxies that we see? No. But they can ask, what about the statistics of the distribution? How much clumps there are? Like if I looked at the distribution of clumped like galaxies, I think where regions where there are a lot of clumps or regions where there are little clumps, what is the statistics of that distribution? And that is what people predict. So what they do, for example, is so our universe, the place where galaxies sit, and in fact, the very existence of galaxies themselves are actually dependent on something called dark matter that we cannot see, but we feel its gravitational pull. In fact, there's more dark matter than there is visible matter, and dark matter creates little kind of pockets of gravity where the rest of the matter can kind of gather and ignite and create galaxies. So the galaxies wouldn't be on if it wasn't for dark matter. And where the dark matter is densest is also going to be where the galaxies are densest.
Wait, what is black matter? Dark matter?
We don't know, but it's some stuff, okay?
Is it like atoms? Or?
No, we don't know. It could be as complex as atoms or as simple as a single new
They call
particle.
it dark because they don't know what it is.
Yes. They call it dark because we can't detect it, we can't touch it, we can't grab it with anything. But we feel its effect gravitationally. But we know that we know things about it. We know that it, for example, doesn't interact much with itself, and most of its interactions are gravitational. And oops, from that we can actually simulate it. So here's a simulation of dark matter.
So it doesn't interact with itself, it means it doesn't pull itself together?
It doesn't pull itself by an additional force except for gravity. Of course it interacts with itself gravitationally. So when you do a simulation like this with some generic initial condition, you see that there's going to be some statistics associated with how many objects of this size there are, how many objects of that size there are, how many objects of this size there are.
But what are the orange glowing?
There are clumps of dark matter. So they're like basically, there are places where dark matter kind of coalesced into a bunch that created sort of a bound state, like a solar system, for example. They're very tight, right? And then what you do is you don't compare the picture to the other picture. Like you're not going to compare this picture to this picture. That's going to be meaningless. But you can compare the statistics of how many of these guys of a certain size there are to the actual measurements. So these curves are basically various choices for cosmological parameters, and what they're showing is that for certain choices of cosmological parameters, they agree very well with the statistics of actual measured galaxies out there. So they look at the galaxies, they survey them, in fact, they're called galaxy surveys, and they calculate the statistics of those distributions, and from those statistics, they try to match them with their simulations. Yes?
What are statistics useful for?
This.
But they can't tell us for any particular galaxies. So statistics are good for describing the whole picture, but they can't give us anything specific.
It cannot give us anything specific. It can't say there'll be a galaxy like right in here.
So what is the use of statistics?
Well, the use of statistics is that they actually allow us to say whether our models of the world are correct. So you have to give up on the idea that we will precisely predict the future or precisely predict the configuration. But what we can predict are the statistics of the configuration. So again, we're not going to, for example, ever predict the precise shape of our galaxy. But we will be able to predict, for example, the velocity distribution or something in our galaxy as a function of distance from the center.
So how do you choose what you can, like, you say you can't predict the shape, but you can predict the velocity. Which things?
No, I mean, like, you're not going to be able, people predict also, like, the profile on average. You just can't predict, like, literally if there's going to be a star here or not.
Any singular event.
Any singular, like, detail. But you can predict averages. You can predict, for example, the density profile of our galaxy. Or you can predict the velocity profile as a function of radius. But you can't predict, like, specifically, is there going to be a star here or not.
But you can also predict future, right?
You could predict the evolution of the probability. But you can't predict literally what's going to happen.
Anyway, it's very useful statistics because you know that from 4 to 6 there's going to be traffic, even though you don't know if this blue car is going to be there.
Exactly.
Right?
Oh, that's so perfect. It's like, Jeannie, I just like planted you here because I'm about to show you, we all agree that Mexico is chaotic, but there's in fact a mathematical rigorous proof that that's true. So there's a particular town in Cuernavaca, I don't know if any of you have been there, but apparently the bus drivers of Cuernavaca are just private. There's no coordination between them. It's not like there's a bus company.
It's like that in South Africa.
Is that true?
Yeah.
Okay, so I guess maybe we should do the same study. So this is the spacing between the arrival of buses in a particular station. And this probability distribution essentially says that it's kind of maximally random. And it agrees pretty well, so this probability distribution agrees pretty well with the actual data because essentially there's no coordination between the different bus drivers, so they behave chaotically. They behave like a random system. And the same curve occurs in many, many...
Guess the temperature before, huh?
Yes, exactly.
What
like,
is the system coordinate?
This is essentially the probability.
Is it the time and
This is the time, and this is the probability that a bus arrived, like with that spacing in time.
Okay, but you can reduce this within 1 hour, something like that, right?
Yes, within an hour.
It's not like Germany.
It's not like Germany, no, it's Mexico. So the same probability distribution, I didn't talk about quantum chaos, which is even more complicated. But there's a certain randomness that is the same randomness that is prevalent, let's say, in the bus distributions. That randomness also exhibits itself in the quantum world. So in quantum world, you have energy differences, let's say, within the nucleus. And for people who know things about atoms, you know that the spectrum of the atom depends on the differences of energies, like the electron is excited to. In nuclei, it's the nuclei that have energy differences. But if you look at their energy differences in a very complicated system like this, again, they have a particular probability distribution which is essentially the same as the one governed by the buses. Again, you can do this for various quantum versions of the billiard game that I showed you. So these probability distributions, like they really characterize the system. So what's amazing about chaos is that there's a certain universality. Like you don't actually need to know. You can't know the specific histories. But what's amazing about it is that probability distributions govern things, and so there's a certain universality.
Wait, is chaos the same as entropy though?
Okay, good. Wow.
Whoa.
Whoa.
Do you know each other?
I didn't show her this. Like
Yeah,
I swear to God, I
supposed to
didn't
know
tell it to
chaos.
Jeannie either.
chaos.
Oh my God.
I'm agreeing with you.
That's amazing. Okay, so I wanted to explain a little bit about entropy. So chaos is very much related to another concept called entropy. And so I want to tell you a little bit what entropy is, and I want to explain this. Okay? So, as we said, what chaos does is it essentially erases history as perfectly as it can.
Like in the water.
Like with the water. So now you really cannot tell at all where we dropped it.
Yes, but you can tell by the spread of it that it's most likely at the bottom. You dropped it maybe 30 minutes ago.
Right, but you know, like you will not be able to tell. I mean, I don't know. I can't really
Precise
tell.
location.
It's hard to tell
We need
already.
to turn the lights, we can examine it.
You can examine more closely. I don't think you
A
can
little
sort
bit on
of
top.
a little bit more, but okay, wait for another 30 minutes or something. Depends on the time scale. It's hard to tell already precisely what it was. So essentially, what happens is that chaotic systems, they evolve into a final state which is as random as possible given the constraints, right? When the ink was inside of here, it was constrained to be in this bottle. It couldn't move out. When we put it in the water, suddenly its lifestyle got grander. It had more possibilities to explore, and it was basically said, I'm just going to go wherever I can. I'm just going to explore my world. So that's what chaos does. It explores things as essentially democratically as possible. So the chaotic dynamics causes basically systems to cycle through configurations democratically. And so this is where the concept of entropy is useful, because if you know that what it's going to do is just cycle through all configurations democratically, you can ask now questions about statistics. Like, how likely is it for me to find myself in a mixed configuration as opposed to a configuration where everything is concentrated in one place? So, in fact, our notion of evolution in time is really related to precisely what we're seeing here. It's related to the fact that we know that certain configurations are more likely in the future than in the past. And that is related to something called the second law of thermodynamics. So if n is the number of configurations that are accessible at any point, and you take the difference between the initial and the final, the difference always increases. That's the second law of thermodynamics. So more and more and more configurations are always explored with time. And so let's just do like a little count. Like we're going to do a simple version of this experiment like right here. So imagine that I just turn this thing to the side, and instead of having like lots of molecules and atoms in there, I'm going to just have 9. And so this is for me like the ink concentrated in a particular place, whereas this is the ink kind of distributed, right? And I can count. I can say, if it's moving through configurations democratically, what is the likelihood? How many configurations are there where these guys are together? Well, the number of such configurations which are kind of ordered because they're kind of together, there's 7. How many configurations which are not ordered or mixed? There are 84. So there are many more configurations that are mixed than there are configurations that are ordered. So if it's just moving through them democratically, the chances that you are going to be at any given point in an ordered configuration is somewhat low. But now let's ask, what's going to happen if we multiply the size of the system by 10? Right? So imagine that instead of having 9, I now have 90. So I have 90 boxes in here.
But aren't the...
And 30 here. So imagine that this is 90 and 30. So I can ask how many ordered configurations, then there are roughly 60. Okay? So very roughly there'll be 60 ordered configurations.
I have a question. Aren't those 60 or 7 ordered configurations also counted by the 84 mixed?
Yes. So you're asking what percentage of the mix are ordered.
Yeah. And why is this important in real life?
Because in any given time, what's happening is that it's just cycling through configurations democratically. It's just moving from them. It's just as likely to be in any configuration as any other configuration, but it's just that there are only 7 configurations where you would say, oh, the ink is together, whereas here we're 7 out of a total 84 configurations. So most of them are mixed.
Yeah.
So now we can ask what happens if instead of 3 and 9, it's 30 and 90, and what is this mixed number going to be?
So I know how to multiply by 10, and I bet you it's not 60, but 70. Not that it matters.
No, it's, okay, damn it, all right. This is 6 plus 1. It's because this is really 61. Count it. It doesn't matter. What?
That's not.
That's arithmetic, that's not math.
Yeah, because there's a 1 shift over. It doesn't matter. It's a little small thing. So how many of total configurations there are if there are 90?
84,000?
No. 7 times 10 to the 23.
What?
What?
Yeah.
So now what is the chance of finding yourself in one of those? Like nothing. Even with only 90 guys. I'm not even talking about like Avogadro's number worth of things. Why? Because this thing scales linearly with the volume. So that is the number of configurations here depends on the volume. This one scales exponentially.
Wait. Why is it 7 times 10 to the 23rd?
Do the calculation. I'll tell you later. It's exponential in the volume. You can count.
Isn't it just 9 times 8 times 7?
Well, they're 90 now. And there's
Yes.
30. You're asking,
It's also 30.
calculate this. Do you know what this means?
Yeah.
Okay, find it. It's 10 to the, it's this. All right?
Plus 1.
Whatever.
So what is 10 to the 23rd power?
It's like really freaking big. It's like really big.
Like a billion?
No. No. It's like a billion billions. It's a
Billions of
billion,
billions of
billion.
billions.
It's a lot. It's a lot. Okay.
No.
Good.
10,000.
So
How many zeros?
all right. So
100 million,
So that's 10,000 billion.
Less than.
right. So essentially, this is what entropy is about. Entropy is related to the number of configurations. So light for a sec. All right. Thank you. So what is entropy? Entropy is just counts the configurations. And because the configurations grow very quickly and they grow exponentially with the volume, actually it makes sense to define the entropy in terms of an exponent. So the entropy is this, it's something called S, but the exponential of the entropy is the number of configurations. So morally speaking, like the number of configurations is the same as entropy, and when people say the number of configurations increases or the entropy goes up, that's what they're talking about. They're talking about the second law of thermodynamics. So maybe then, since it's been a while, let me end.
I mean, but let's like if there's like a magnet, strong magnet, right? And you drop a whole bunch of balls that are metallic. Eventually, everything will concentrate on the magnet. Right? You know, they might have bouncing around. So that's kind of the opposite of that, right? Because everything will be.
Well, I mean, there are other things. I mean, the entropy is not just counting those objects. It's counting those objects and the rest of the things that there are in the universe, right? So the claim is that when the entropy increases, it's not the entropy of a particular system, it's the entropy of everything.
Right. But what I'm saying is that there are forces, right? And these forces kind of constrain
Yes.
your choices.
Yes, so they can constrain the choices of some specific system, right? Like this pendulum is not going to just fly away suddenly, completely fly away. So there are always going to be restrictions on the configuration. So it explores as much as it can given those restrictions. But but it doesn't mean that entropy is not.
So basically, what this law says is in 10 seconds, there's going to be a lot more possibilities than in 1 second.
Exactly. So let me just maybe conclude, since it's been a while, and instead of explaining like a couple more things, let me just finish because think I've covered a whole bunch of ideas. And then we can talk in private if you want a little bit more about.
From the place where the people who don't have good grades.
So why are we even here?
Good question.
Whoa, whoa! Why is it possible for us to live? Because the initial conditions of the universe were at an incredibly low entropy. We are here because we're still exploring the space of possibilities. We're like the ink that was pretty concentrated and still had a lot of intricate filaments to go through, a lot more things going on before it just became this kind of uniform thing. So for some reason that we don't understand, the initial condition of our universe was very, very ordered. What?
What happens when the ink? What happens when the ink mixes all into the water?
Yeah, so the analog of that, like what is going to happen to us in our universe eventually, that's what you're asking?
Yeah.
Yeah.
We're all going to become black holes.
Uh-oh.
So there's a separate lecture. I actually have to explain to you, but black holes are the highest entropy configuration.
So what about progress?
Progress is those little filaments. Those little
Better
filaments.
organization, right? So
Right.
progress is counter to the fact that as we go through time, the predictability becomes more and more uniform, right? So the entropy increases.
The entropy increases. We're
we
using
have progress,
energy
though.
to
we have
organize.
computers, we are more better organized than 200 years ago.
Right, because we are life forms, right? So we dump entropy into the environment, use energy, right? But eventually we're going to run out of energy in a useful form, such that we won't be able to anymore not just work anything, but we won't be able to make memories. We will reach equilibrium. At that point, we can't record anything, we can't talk about anything, it's over. But there's a lot of time to party, it's still good. Like we're still in the phase of creative exploration of configuration.
That's what you're saying.
Where was the drop phase? Yeah, that's what's amazing about our universe. We're still in the creative filaments of, so go and explore your configuration.
For generations and generations.
Maybe it's a good time for stuff.